Hello, Professor and everyone. My name is Nguyễn Thế Vĩ. I, together with two other students, Nguyễn Thị Mỹ Tuyên and Hứa Đức Thiện, will present the Chapter 9, Publication. This is outline of my presentation. I will go through two sets of principles that have been proposed to guide the publication of data on the web. Now let's go to the introduction of publication of knowledge graph. The question is, what is the knowledge graph publication? Knowledge graph publications refers to making the knowledge graph accessible to the public, often on the web. And the second question is, which publishing principles does knowledge graph publication rely on? The answer is there are two sets of principles. The first principle is FAIR principle and the second one is linked data principle. Now let us discuss the first set of principles. FAIR principle was originally proposed in the context of publishing data or scientific data, particularly motivated by maximizing impact of publicly funded research. But the principles generally apply to other situations where the data are to be published in a manner that facilitate their reuse by external agents, with particular emphasis on machine readability. Here, FAIR is an acronym for four foundational principles, each with particular goals, and they are findability, accessibility, interoperability, and the last one reusability. Let us discuss the findability first. So findability refers to the ease with which external agents can who might benefit from the dataset can initially locate the dataset. Four sub-goals should be met. The first sub-goal is meta and metadata and data are assigned a global, unique, and persistent identifier. Here, metadata are the data about data. For example, in astronomy, data may include the raw image data, while metadata may include the coordinates and time. Now we come back to the second subgoal. The data are described with rich metadata, and the third one is metadata explicitly include the identifier of the data they describe. The last subgoal is metadata and data are registered or indexed in a searchable resource. For a second principle in FAIR principle is referred to the ease with which external agents can access the data set after locating it. Two goals are defined, and the first goal with two subgoals. Here, the first goal is that metadata and data are retrievable by their identifier via standard protocol. So, this first goal have two subgoals. First subgoal is the data is open, free, and universally implementable. And the second one is the protocol use authentication and authorization if suitable. For the second goal, the meta are accessible and even when the data are no longer available. For interoperability, um, it refers to the ease with which dataset can be exploited in the union with other datasets using standard tools. Three goals are defined. The first one is the metadata and data used accessible, agree upon, or general knowledge representation formalism. The second one is metadata and data use vocabularies that follow FAIR principles. And the last one is metadata and data include qualified references to other metadata and data. For the reusability, it refers to the ease with which the dataset can be reused in conjunction with other datasets. Uh, there are several rules that can be defined as follows. The first one is the metadata, and data are richly described with accurate and relevant attributes. In this goal, we have three subgoals. The first subgoal is metadata and data are released with a clear and accessible license. Second one is metadata and data are associated with detailed provenance. And the last one is the metadata and data meet domain relevant community standards. Before continuing with the FAIR principles, we recall some definitions related to the resource description framework. The resource description framework is framework for representing the information in the web, and the core structure of the abstract syntax is a set of triples, each consisting of a subject, a predicate, and an object. And a set of triple is called an RDF graph. And an RDF graph can be visualized as a node here and direct diagram in which each triple is represented as the node link here as shown here. And there can be three kinds of nodes in an RDF graph: IRI, literal, and plain nodes. Here, the IRI stands for Internationalized Resource Identifiers, which allow the global identification of entities on the web. Literal is the term allowed for representing the string with or without language text and other data type, value, integer, or dates. And plain nodes are anonymous nodes that are not assigned an identifier. So now we come back to the FAIR principle that used this kind of term, this kind of framework. The question is how can knowledge graph application can be certified the FAIR principle. So variety of vocabularies, tools, and services have been proposed that both directly and indirectly help to certify the FAIR principle. In terms of findability principle, the IRI are built into the RDF model, and REI, RII, and RDF model are the terms as I define here. Under this one, they can provide the general schema for global identifiers. In terms of accessibility, some access protocols will be discussed in section 9.2, while a mechanism for authorization will be discussed in section 9.3. In terms of interoperability, ontologies can serve as the general knowledge representation formulation and can in turn be used to describe vocabularies that follow the FAIR principle. And the last one, in terms of reusability, we can use the licensing, which is discussed in section 9.3. Now we go to the second set of principle, that is linked data principle. Wilkinson in 2016 stated that the FAIR principle that I mentioned above, it do not cover how they can and should be achieved. So preceding the FAIR principle, the linked data principle were proposed by Benelli 2006, which proposed to provide the technical basis for one possible way in which the FAIR principle can be achieved. The linked data principle are listed as follows. There are four principles. The first one is use IRI as the name for things, and the second one is use HTTP IRIs, so those names can be looked up. And the third one is when the HTTP IRI is looked up, provide useful content about entity that the IRI names, use standard data formats. And the last one include links to the IRIs of the related entities in the content return. So now we go to the example for the linked data principle. In the figure below, there are two linked data documents published on the web, with each contain an RDF graph. The term suggests CLV concert or WQ14270 like this, abbreviation for the IRIs, where, for example, W here, WDQ14270 expand to this kind of link, and prefix begin with the CL are prefix that assumed to have been created by the Chilean Tourist Board, and the IRS prefix with this notation indicate that the document return if the node is looked up, and the H label with also the IRIs and node representing the class. For example, this one can be the references, typically returning the semantics and the definition of the respected term. Now we consider the leftmost documents here. Is published by the tourist board and describe the lab Lollapalooza 2018, identified as this cap node. This node linked to the headlining Pew arm here, Pew's jam here. This node described by the external knowledge graph, namely the Wikidata. By looking up the node like this one in the leftmost graph, the IRIs dereference returned via HTTP. The document with the RDF graph on the right, describing the entity for more detail. From the rightmost document, the node this node can be looked up in turn to find a graph about the eddy feeder. This is not showing an example, but the IRIs for the entities and documents are distinguished to ensure that we do not confuse data about the entity and the document. For example, WD here 2Q221535 refers to the SD vector, and the IRIWDDD here refers to document about the SD vector. We have to distinguish between two terms here. And if we were assigned to the last modified date to the document, we should use WDD instead of WD. And a key challenge is posed by the fourth principle. Here, fourth principle in the linked data principles is include a link between the link to the related entity. For example, here we have two entities related to each other, and so how to deal with this challenge? Specifically, we can use the link discovery task, which is consider adding the search link from one knowledge graph to another one. This one is one knowledge graph and this one is another one. So how we can link together? The approach is that we use the link discovery.
This is the outline of my presentation. I will go through 5 access protocols that are used for publishing of knowledge graph. In this slide, I show you the introduction to access protocols. Publishing involves giving access to the public to interact with the knowledge graph, which implies the provision of access protocol that define the request that agent can match and the response that they are expected as a result. In Figure 9.2, there are a number of access protocols to choose from, varying from simple protocol that allow users to simply download on content to a more complex protocol that access and evaluating increasing complex requests. While simple protocol require less computation on the server that publishes the data, more complex protocols allow agents to request more specific data, thus reducing bandwidth. Now, let's consider DUMS protocol first. A DUM is a file or collection of files containing the content of knowledge graph available for download. The request in this case is for the files and the response in the content of the files. In order to publish them, first of all, concrete and ID standard syntax are required to serialize the graph. Second, to reduce bandwidth, compression methods can be applied. Finally, to further reduce bandwidth, when the knowledge graph is updated, this can be computed and published. Average the need for agent to download on data from scratch. However, DUMs are only suited to certain use cases, in particular for agents that wish to maintain a full local copy of a knowledge graph. If an agent were rather only interested in, for example, on food festival in Santiago, downloading the entire DUM may request transferring and processing of a lot irrelevant data. Next, we consider second protocol, not lookups. Not lookups are protocols for performing not lookups accept a not ID request. For example, CLA LP 2018 in Figure 9.1 and return a subscript describing the not example the document CLD LP 2018. Such a protocol is the basis for the linked data principle outlined previously, whereby not lookups are implemented through HTTP dereferencing, which further allows not in remote graph to be referenced from across the web. Mechanism for evaluating graph pattern can be implemented on top of a not lookup interface by traversing from node to node per the particular graph pattern. For example, to find on food festival in Santiago represented by the graph pattern like this. We perform a not lookup for Santiago subsequently performing a not lookup for each node connected by a local X to Santiago, returning those nodes declared to the Thai food festival. However, the client agent may also need to request more data than necessary. For example, the document returned for Santiago may return a lot of data irrelevant to the query and not with a location in Santiago that are not instance of food festival still need to be looked up to check their time. Not lookups are relatively inexpensive for servers to support the term of CPU, but may again waste bandwidth due to transferring irrelevant data. Next, we consider third protocol H patterns. H pattern, also known as triple patterns, in the case of directed H labeled graphs, are singleton graph patterns. That means graph patterns with a single H. Symbol of H pattern are like this and this, where any term can be a variable or a constant. A protocol for H pattern accepts such a pattern and returns on solution for the patterns. H patterns provide more flexibility than not lookups, where graph patterns are more readily decomposed into X patterns than not lookups. For example, with respect to the agent interested in food festival in Santiago, they can first, for example, request solution for the X pattern like this and locally join interface the solution with those pattern like this. But this not lookup, the server cost of responding to requests is relatively low and easy to predict. However, the server may often need to transfer equivalent intermediate research to the client, which in the previous example may involve returning not local in Santiago that are not food festival. Next, we consider fourth protocol, complex graph patterns. Another alternative is to let client agents to make requests based on complex graph patterns, which the server returns link only the final solution. Example, this involves the client issuing the request for person like this and directly receiving the relevant results. Compared with the previous protocol, this protocol is much more efficient in terms of bandwidth. It allows clients to make more specific requests, server to return more specific responses. However, this reduction in bandwidth use comes at the cost of the server having to evaluate a much more complex requests, where furthermore the cost of single requests is much more difficult to anticipate. Finally, in this slide, we present some other protocols. While figure 9.2 make explicit reference to some of the most commonly encountered access protocol found for knowledge graph in practice, one may count in much other protocols lying almost anywhere on the spectrum from more simple to more complex interface. To the right of complex graphs fashion, one could consider supporting even more complex requests such as querying with entailment reference like this. Query the dash allow precaution. As mentioned at the outset, a server may also choose to support a multiple complementary protocol.
So now we will move into the usage control section. One might assume that the knowledge required to deliver the service is public and thus can only be used both by the tourism board and the tourist. We may see the need for usage control in the considered tourism knowledge graph here, in which both of the tourist board and its partner should associate an appropriate license with knowledge that they contribute to the knowledge graph, such that the terms of use are clear to all interest parties. To a tourist might eager to install an app on their phone that could be used to recommend tourist attraction based on their location, bringing with it potential privacy concern regarding to who has access to their location. And the tourist board may be required to report criminal activities to the police service and therefore may need to encrypt their personal information. And the tourist board could potentially share information relating to tourism demographics in an anonymous format to allow other agencies and companies to anticipate demand and improve transport infrastructure on the strategic roads. So therefore, in this section, we will examine the state of the art in terms of knowledge graph, licensing, users policy, encryption, and the last one is the anonymizations. And we will move to the licensing section. The W3C's Open Digital Rights Language, which is proposed by Lanella and Villata in 2018, provides an information model and related vocabularies that can be used to specify permissions, duties, and prohibitants with respect to actions relating to access. This namely ODRL support a fine-grained description of a digital rights that are present as a crafts. Here, figure 9.3 illustrate a license granting the assignee to the assigning the permission to modify, distribute, and deprive a work from the event craft, but the assignee uh, have to be attribute the copyright holder. So from a modeling perspective, the open digital rights language can be used to model several well-known public copyright license companies, such as the Apache, the Creative Commons, and the Berkeley Software Distribution. And these are the logos of those firms. Caprio and his college has proposed methods to automatically extract the machine readable license from unstructured text, and those have been mentioned in the book entitled "These Are Your Rights." This is a natural language processing approach to automated RTF license generation. The license compatibility validation and composition like techniques can be used to combine knowledge graph that are governed by different license, and these have been denoted in the work of Governatory, Montreal, Vilata, and Camden. Such techniques are employed by the Data License Clearance Center, which include a library of standard machine readable license and tools that enable user to both compose random custom license and also verify the compatibility of different license. This is the logo of the Data License Clearance Centers. This is a license management framework for digital assets. Here, the access control policies is based on the edge pattern that can be used to restrict access to part of a knowledge graph. The web access control here is the decentralized system for allowing different user and groups varies from to access to the resource where the user and group are identified by the HTTP URI. Here I given the diagram here. This give the readable access to the web ID profile document. Specifically this document, the 2013 card, but only give a limited access of this resources, namely the protected one here. And to these are given the access to the member of a group that went to a particular conference. The system is similar to the access control system used in many file system, except that the document here are being controlled. The user and the group are all identified by the URI. The user are identified by the web ID, and the group of users are identified by the URI of the class of a user, which return a list of those users in one class. This means a person can host by any site can be a member of the group hosted by another site. And you can give access to the document on one site to the user and group hosted by another site. User do not need to have the access to the document on it. And in order to be able to share a common code and a common ontology is proposed, which provides the terms necessary for access control list to be stored. Each request for a web resource return an HTTP document like this here, containing a link reader to a link header to an ALC resource, which describe access to given resource and to the others. And this is what the diagram. This is what is the diagram want to describe. Although the ODRL is primarily used to specify license profiles to additionally specify access policy proposed by these people, and the regulatory obligation here has also been proposed in a recent year and is discussed in the survey which is proposed by the Karen and his college. As a generalization of access policy, the usage policies is specify how data can be used. What, like, for example, like what kind of processing can be applied and applied to whom, for what purpose. The example of the usage policy presented in this figure 9.4 here state that the process that analyze of the location graph can be performed on an internal server by the members of the company staff in order to provide the event recommendations. The vocabulary for the usage policies have been proposed by the Special H 2020 project proposed by Ponari and his colleague, and the W3C data privacy vocabulary and the control community group. One specified in these vocabularies, the usage policy can then be used to verify the data process, conform to legal norms, and to the consent provided by the subjects. This quote has been mentioned in the special usage policy language version 1.0 and by Ponari and Kereni, and in the query-based link data anonymizations proposed published by Delanos. So we move to the encryption properties. Rather than internally controlling usage, the tourist board could use encryption mechanism on parts of the published knowledge graphs, in which including, for example, like the crime reports, provide key to the partner who have access to the plain text. For example, the straightforward approach is to encrypt the entire graph or a subgraphs with one key. A fine-grained encryption can be performed for individual nodes or edge label in the graph, and potentially providing different license access to different information through a many other different keys. And these are cited from the on partial encryption of the RDF graph published by the QREF. Another crypt ontology proposed by Gerbrand can be further used to embed details about the encryption mechanism used within the knowledge graph. Here, the figure 9.5 illustrate how this could be used to encrypt the name of a claimant, storing in the ciphertext, for example, this ciphertext, as well as the key length and the encryption algorithm is used. In order to grant access to the plain text, one approach is to encrypt the individual edges with symmetric keys, allowing specific types of edge pattern to only be executed by clients with the appropriate keys. So this approach can be used, for example, to allow the clients who know the claimant, for example, that this claimant here have the appropriate key to find the name of the claimant through the edge pattern. However, the key limitation of this approach is the requirement of attempting to decrypt all the edges to find all the possible solutions. Another efficient alternative proposed by Fernandez and his colleague is to combine functional encryption and specialized indexing to retrieve a solution from the encrypt graph without attempting to decrypt all of the edge in the in the graph. So we will move to the anonymization properties. So consider that the tourist board acquired information on transport taken by individual within the country, which can be used not only by the board, but potentially by another stakeholders, such as the agency, the companies, to understand the trajectories taken by the tourist. So from a data protection perspective, it could be advisable to anonymize the knowledge graph to avoid leaking the personal travel history of one person. The first approach to anonymizations is to suppress and generalize the knowledge in a graph such that one tourist cannot be identified. It could be based on the k-anonymity proposed by Samarati and Sweeney, in which they are guarantees that the data of a tourist is indistinguishable from at least uh, k, the total number of k minus one other tourists, and L diversity here guarantees that the sensitive data fields have at least L diverse value within each group of individuals, and this avoid the leaks such that all the tourists from, for example, um, from the Austria in the data have been pickpocketed in a sensitive attribute, which would reveal the sensitive information of the tourist from the Austria. So the approach that apply the k-anonymity on graphs identify and suppress namely quasi identifiers that would allow a given individual to be distinguished from the other numbers, the total number of the tourists, except one is except the mention, the considered tourist here. So the figure 9.6 illustrate a possible result of k-anonymizations for a subgraph describing a flight passenger here, where the quasi-identifier, like in this graph, is the passport and the plane ticket have been converted into a plane note here, ensuring that the passengers cannot be distinguished from the others. In the context of a graph, neighborhood attacks propose this is mentioned in the work of Zhou and Pei, using information about neighbors can also break k-anonymity, where we also suppress the day and time of the flight, which although not sensitive information, could otherwise break the k-anonymity for passengers. For example, a particular flight might have fewer than the k number of males from the US on board. So the graph shown in 9.6 then offer a k anonymity for particular individual, assuming that at least k number of male passengers from the US flew during the December 2018 from Africa to San Diego. A more complex normal neighborhood attacks might rely on abstract graph patterns, observing that the tourists can be de-anonymized purely from the knowledge of graph structure, even if all nodes and edge label are left blank. For example, if we know that a team of a flight tourism take flights together for a particular number of the games and a total number of players in the game, we could use this information for neighborhood attack that reveals the setup layer in the graph. So uh, therefore the number of guarantees specific to the graphs have been proposed. For example, like those techniques here. First is the k-degree anonymity proposed by Liu and Terzi, ensure that the individuals cannot be anonymized by attackers with knowledge of the degree of the particular individuals. The approach is based on the minimally modifying the graph to ensure that each node has at least k minus 1 other nodes in the same degree. And another one is the stronger guarantee k isomorphic neighbor anonymity proposed by Zhou and Pei. Avoid neighborhood attacks where attackers know how a person is connected to a node in their neighborhood. This is done by modifying the graph to ensure that for each node there exists at least k minus 1 nodes with isomorphic namely the identically structured neighborhood or elsewhere in the graph. The last but not least is the k automorphism proposed by Zhou and his colleague, ensuring that for every node it is structurally distinguishable from k minus 1 other nodes, thus avoiding any attack based on the structural information. For example, like k-clique, k-cycle satisfy, k-automorphism. These approaches not only protect against the attacker with knowledge, these are only protect against the attacker with knowledge of the bounded neighborhoods. Many of the techniques for anonymizations of graph data were motivated by the social networks, which is mentioned in the work of Narayanan and Smartkov, though they can also be applied to knowledge graph. The work of Lin and Tripuni Terra, they adapt the K automorphism for direct edge label graphs, especially the RDF graphs. While the aforementioned techniques anonymize the data, this approach what we will discuss here is to apply anonymizations when answering queries, such as adding noise to the solution in a way that preserve the privacy. So, for example, in the language and automata language and programming proposed by Dwork have applied the epsilon differential privacy for querying graph. This epsilon differential privacy ensure that the probability of a given result from a process, which is a query, applied to data to which random noise is added. This is differ no more than the exponential of epsilon value when the data include or exclude any person, any individual. So to illustrate the differential privacy here allow for counting the number of passengers of specified nationalities taken specific flights by adding just enough random noise to the count to ensure that we cannot tell within a certain probabilities in here is controlled by the value epsilon whether or not a particular individual took a flight where we could require proportionally less noise for the nationalities with many passenger in the data, but more noise to hide the passenger from the uncommon nationalities. So this approach requires information loss for a stronger guarantee of privacy, and this is a burden to choose which approach to be used, and therefore it's required a more heavier application. If the anonymized data are to be published in their entirely as a term, an approach based on K anonymity can be used to protect individual, while the L diversity can be used to protect a data of the groups. And if a data are able to make available or through a query interface, the epsilon differential privacy technique is a suitable framework to be applied on. And this is the end of the section 9.3.